In the vast darkness of space, there exists a telescope unlike any other, a marvel of human ingenuity floating silently 1 million miles from Earth. The James Webb Space Telescope drifts in the cosmic void, its golden mirrors catching starlight that has traveled for billions of years. This is not just a machine. It is humanity's most powerful eye, designed to peer back through time itself, to witness the birth of the very first galaxies when the universe was young. Imagine yourself floating beside this magnificent observatory, suspended in the eternal quiet of space. The telescope's primary mirror stretches 18 feet across, composed of 18 hexagonal segments made of beryllium and coated in a microscopically thin layer of gold. Each segment gleams with a warm, honeyed light, perfectly positioned to capture the faintest whispers of infrared radiation from the cosmos. The gold coating is no mere decoration. It reflects infrared light with exceptional efficiency, allowing Webb to see what visible light telescopes cannot. The telescope resides at a special location called Lagrange Point 2, a gravitationally stable position where the gravitational pull of the Earth and Sun balance perfectly. Here, Webb orbits the Sun in sync with Earth, maintaining its distance while staying in the shadow of our planet, shielded from the Sun's overwhelming brightness by a tennis court-sized sun shield. This shield, composed of 5 layers of material thinner than a human hair, keeps the instruments at a frigid minus 370 degrees Fahrenheit, cold enough for the sensitive detectors to distinguish the faint heat signatures of ancient galaxies. The journey to this moment began decades ago, when astronomers dreamed of a successor to the Hubble Space Telescope. Hubble had revolutionized our understanding of the universe, but it observed primarily invisible light, the same light our eyes detect. The earliest galaxies, however, exist so far away that their light has been stretched by the expansion of the universe itself, shifting from visible wavelengths into the infrared spectrum. To see these ancient structures, humanity needed a new kind of telescope, one designed specifically to capture infrared light. Engineers and scientists from NASA, the European Space Agency, and the Canadian Space Agency collaborated for more than 2 decades to make this vision real. They faced countless challenges: how to fold a mirror larger than any rocket could carry, how to deploy it perfectly in space, how to cool instruments to temperatures where even air would freeze solid. Each problem required innovative solutions, pushing the boundaries of what was technologically possible. The telescope launched on Christmas Day, 2021, aboard an Ariane 5 rocket from French Guiana. For 30 days, it traveled outward, unfolding like an intricate origami sculpture, the sun shield extending, the mirror segments locking into place, each movement executed with millimeter precision. Controllers on Earth watched nervously, knowing that a single failure could doom the entire mission. But Webb deployed flawlessly, a testament to the dedication of thousands of people who had poured their expertise into every component. After 6 months of calibration and testing, aligning each mirror segment with nanometer precision, the telescope opened its infrared eye and began to observe. The first images stunned the world, galaxies appearing in unprecedented detail, nebulae glowing with hidden structures, stars being born in clouds of gas and dust. But perhaps Webb's most profound purpose lies in its ability to observe the cosmic dawn, the era when the first galaxies assembled from primordial hydrogen and helium, when the universe transitioned from darkness to light. To understand what Webb reveals, we must first grasp the scale of cosmic time. The universe began 13.8 billion years ago in an event we call the Big Bang. For the first few 100,000 years, the cosmos was a hot, dense soup of particles and radiation, too energetic for atoms to form. Then, as the universe expanded and cooled, electrons and protons combined to create the first hydrogen atoms, and the universe became transparent for the first time. This moment, known as recombination, left an echo that we detect today as the cosmic microwave background radiation. But after recombination came a period astronomers call the cosmic dark ages. No stars existed yet, no galaxies, only vast clouds of neutral hydrogen drifting through expanding space. Gravity slowly pulled these clouds together, creating denser regions where gas accumulated. Eventually, these concentrations became massive enough to ignite nuclear fusion, and the first stars blazed to life, perhaps 100 million years after the Big Bang. These earliest stars were different from those we see today. Massive, brilliant, composed almost entirely of hydrogen and helium, because heavier elements had not yet been forged in stellar furnaces. They burned fiercely and died young, many exploding as supernovae and seeding space with the first carbon, oxygen, and iron. Around these stars, the first galaxies assembled, small and chaotic compared to the grand spirals and ellipticals we observe in the nearby universe. The light from these first galaxies has traveled across billions of light years to reach us, carrying information about conditions in the infinite universe. But as that light journeyed through expanding space, the fabric of the universe itself stretched, pulling the wavelengths longer, shifting blue light to red, red light to infrared. The most distant galaxies Webb observes appear as they were when the universe was only a few 100 million years old. Their light shifted so far into the infrared that no optical telescope could detect them. This is where Webb's golden mirrors come into their own, capturing photons that have journeyed across more than 13 billion years of cosmic history. Each image the telescope records is not a snapshot of the present, but a glimpse into the distant past, allowing us to witness galaxy formation as it actually occurred, to see the architecture of the cosmos when it was still under construction. Let's drift backward through time, imagination carrying us to an era before any galaxy existed, to the universe as it was in its infancy. The Big Bang occurred 13.8 billion years ago. Not an explosion in space, but an expansion of space itself from an infinitesimally small, incredibly dense state. In those first fractions of a second, the universe expanded faster than light can travel, a period called cosmic inflation, smoothing out irregularities and setting the stage for everything that would follow. In the beginning, temperatures exceeded trillions of degrees, too hot for even atomic nuclei to hold together. The universe consisted of a seething plasma of quarks, electrons, and photons, all in constant, violent interaction. As space expanded, it cooled, and within microseconds, quarks bound together to form protons and neutrons. Within minutes, nuclear fusion in this primordial fireball created the first atomic nuclei, primarily hydrogen, along with helium and trace amounts of lithium. For the next 380,000 years, the universe remained opaque, a glowing fog where photons couldn't travel far before colliding with free electrons. Then came the moment of recombination, when temperatures dropped enough for electrons to bind with nuclei, forming neutral atoms. Suddenly, photons could travel freely, and the universe became transparent. The light released at that moment still fills the cosmos today, stretched by expansion into microwave wavelengths. The cosmic microwave background that radio telescopes detect as a faint whisper of radiation coming from every direction. But recombination marked the beginning of the Dark Ages, a period lasting perhaps 100 to 200 million years when no stars lit the cosmic night. The universe expanded in darkness, filled only with neutral hydrogen and helium gas, slowly cooling from thousands of degrees to just a few degrees above absolute zero. Gravity, however, continued its patient work, drawing gas toward regions that were slightly denser than average. Tiny fluctuations imprinted during inflation, preserved in the structure of the universe. These denser regions grew slowly, attracting more gas, forming structures we call dark matter halos. Dark matter, a mysterious substance that interacts with ordinary matter through gravity but doesn't emit, absorb, or reflect light, makes up about 85% of all matter in the universe. Though we cannot see it directly, we detect its presence through gravitational effects, the way galaxies rotate, how light bends around massive clusters. During the Dark Ages, dark matter clumped together first, creating gravitational wells into which ordinary gas could fall. Within these halos, hydrogen clouds compressed under their own gravity, growing denser and hotter. When a cloud's core reached temperatures of millions of degrees, hydrogen nuclei began fusing into helium, releasing tremendous energy. The first star ignited, transforming a dark pocket of the universe into a brilliant beacon. These population 3 stars, as astronomers call them, were giants, perhaps dozens or even hundreds of times more massive than our Sun, burning with intense blue-white light. These massive stars lived fast and died young, exhausting their fuel in just a few million years. When they could no longer sustain fusion, they collapsed catastrophically, triggering supernova explosions that briefly outshone entire protogalaxies. These explosions distributed newly created elements, carbon, nitrogen, oxygen, iron, into surrounding gas clouds, enriching the cosmic environment. Subsequent generations of stars would form from this enriched material, gradually building the chemical complexity necessary for planets and eventually life. The first stars also transformed their surroundings in another crucial way. Their intense ultraviolet radiation stripped electrons from nearby hydrogen atoms, creating bubbles of ionized gas. As more stars formed and died, these bubbles grew and merged, eventually ionizing all the hydrogen in the universe. A transformation called the Epoch of Reionization, which concluded roughly 1 billion years after the Big Bang. This process marked the end of the Dark Ages and the dawn of the luminous cosmos we inhabit today. Around the first stars, gravity assembled the first galaxies, small, irregular collections of stars, gas, and dark matter, nothing like the majestic spirals we see in the modern universe. These proto-galaxies were turbulent places, with stars forming rapidly from dense gas clouds, supernovae explosions disrupting stellar nurseries, and frequent collisions as small galaxies merged into larger ones. Galaxy formation was a messy, chaotic process, driven by gravity's relentless pull. Computer simulations allow astronomers to model this era, tracking how dark matter and gas evolve under gravity's influence. These simulations show that structure formation followed a hierarchical pattern. Small objects formed first, then merged to create larger ones, which merged again into still larger structures. This bottom-up assembly continued for billions of years, eventually producing the giant ellipticals and grand spirals that dominate today's universe. But simulations alone cannot tell us what really happened. They make assumptions about dark matter properties, about how gas cools and forms stars, about how black holes grow and influence their surroundings. To know whether these assumptions are correct, we must observe the first galaxies directly, measuring their properties, counting their numbers, studying their evolution. This is where Webb becomes indispensable. Only infrared observations can penetrate the redshift and reveal galaxies as they were in the first billion years of cosmic history. Before Webb, astronomers had caught glimpses of this early era using Hubble and ground-based telescopes, identifying a handful of candidate galaxies from when the universe was 400 to 800 million years old. These observations hinted at surprises. Galaxies appeared larger and more numerous than some models predicted, suggesting star formation might have begun earlier or proceeded more vigorously than expected. But Hubble's limited infrared sensitivity meant these observations remained tentative, requiring confirmation and deeper investigation. Now, with Webb's powerful infrared vision, we can survey the early universe systematically, finding thousands of galaxies from the cosmic dawn, measuring their sizes, brightnesses, and star formation rates with unprecedented precision. Each observation refines our understanding of how galaxies formed, how quickly stars assembled, how the first massive black holes grew, and ultimately how the universe evolved from its simple beginnings into the rich tapestry of structures we observe today. To appreciate what Webb reveals about the first galaxies, we must understand the nature of light itself and how it carries information across cosmic distances. Light behaves both as a wave and as a particle, a photon, traveling at 186,282 miles per second, the universe's ultimate speed limit. When a star emits light, each photon carries energy determined by its wavelength. Blue photons carry more energy than red ones, and infrared photons carry less energy still. When we observe a distant galaxy, we are collecting photons that have journeyed across space for millions or billions of years. Each photon that enters Webb's mirrors began its journey when the universe was younger, carrying information about the conditions in which it was created. A photon emitted by a star encodes details about that star's temperature, composition, and motion. Photons absorbed and re-emitted by gas clouds reveal the presence of specific elements. By analyzing the spectrum of light, how brightness varies with wavelength, astronomers can reconstruct the physical properties of objects billions of light years away. But light traveling through an expanding universe undergoes a remarkable transformation. As space itself expands, the photon's wavelength stretches along with it, shifting toward redder wavelengths. This cosmological redshift increases with distance. The farther a galaxy, the more its light has been stretched. For the nearest galaxies, this shift is subtle, barely noticeable. For the most distant galaxies Webb observes, light originally emitted in the ultraviolet has been stretched all the way into the infrared, a redshift so extreme that the wavelength has increased by a factor of 10 or more. Astronomers measure redshift using the symbol Z. A galaxy at Z equals 1 has had its light's wavelength doubled by cosmic expansion. At Z equals 2, the wavelength has tripled. Webb routinely observes galaxies at Z equals 10 or higher, meaning their light has been stretched to more than 11 times its original wavelength. For these objects, emission that started as energetic ultraviolet light arrives at our telescopes as mid-infrared radiation, completely invisible to our eyes or to optical telescopes like Hubble. This redshift is not just a curiosity. It provides a direct measurement of cosmic distance and look-back time. By observing galaxies at different redshifts, astronomers can study cosmic history at different epochs, watching how galaxies evolve as the universe ages. Webb's infrared sensitivity allows it to reach higher redshifts than ever before, accessing epochs that were previously hidden from view, revealing the universe when it was just 2 or 3% of its current age. The telescope's instruments dissect light with exquisite precision. The near-infrared camera, or NIR cam, captures images across wavelengths from 0.6 to 5 microns, just beyond what human eyes can see, extending into the mid-infrared. These images reveal galaxies in stunning detail, showing structures that formed when the universe was only a few 100 million years old. The near-infrared spectrograph, NIR spec, splits light into its component wavelengths, creating spectra that reveal the chemical composition, temperature, density, and motion of distant objects. Another instrument, the mid-infrared instrument, or MIRI, extends Webb's vision to wavelengths up to 28 microns, detecting even cooler, more distant sources. MIRI's detectors must be cooled to just 7 degrees above absolute zero, colder than anything else on the telescope, requiring a dedicated helium refrigerator that hums quietly in the darkness, maintaining the temperature necessary for these sensors to operate. Together, these instruments give Webb unprecedented ability to study the infrared universe. When Webb observes a distant galaxy, it doesn't simply take a picture. The telescope may stare at a single tiny patch of sky for dozens of hours, collecting photons one by one, building up an image from the faintest whispers of light. Many galaxies at extreme distances are so dim that only a few photons per hour reach the detector. Patience is essential. Only by accumulating light over long exposures can Webb reveal these ancient structures hidden in the cosmic dark. The process requires extraordinary precision. Space is not empty, but filled with a faint zodiacal light. Sunlight reflected off dust in our solar system. Cosmic rays, high-energy particles from supernovae and other energetic events, constantly strike the detectors, creating false signals that must be identified and removed. Software algorithms process the raw data, subtracting backgrounds, correcting for instrumental effects, calibrating wavelengths and brightnesses. Only after this painstaking analysis do the final images emerge, revealing galaxies as they truly are. Each image Webb captures is a time machine view, showing not where galaxies are now, but where they were billions of years ago when their light began its journey. The universe has continued expanding during those eons. The galaxies we see at z equals 10 are now much farther away than the light travel distance suggests, carried outward by cosmic expansion. In fact, those galaxies now lie more than 30 billion light-years distant, far beyond the reach of their light, which has only traveled for 13 billion years. This interplay between light, expansion, and time creates the fundamental framework for observational cosmology. Every photon is a messenger from the past, and Webb is humanity's most sensitive receiver, designed to catch and decode these ancient signals. The telescope's golden mirrors gather starlight that left its source when a universe was in its infancy, when the first galaxies were just beginning to assemble, when most of space remained dark and unexplored. In the following chapters, we will explore what these photons reveal, the shapes and structures of the first galaxies, the stars that populated them, the black holes lurking in their centers, and the ways these early systems grew and evolved. We will trace the cosmic story from darkness to light, from simplicity to complexity, following the ancient photons that Webb captures, one by one, building our understanding of how the universe became the magnificent, star-filled expanse we see today. In July 2022, humanity received its first glimpse through Webb's infrared eye when NASA released the telescope's initial images. Among them was a view that would become iconic: Webb's first deep field, showing a galaxy cluster called SMACS 0723 as it appeared 4.6 billion years ago. But this image revealed far more than the cluster itself. It showcased thousands of galaxies scattered across the cosmic background, including some of the most distant ever observed, their light stretched and magnified by the gravitational lens effect of the massive cluster. A deep field observation represents one of astronomy's most powerful techniques, pointing a telescope at a seemingly empty patch of sky and staring for hours or days, allowing faint, distant objects to gradually emerge from the darkness. The original Hubble Deep Field, captured in 1995, revolutionized our understanding of the distant universe by revealing thousands of galaxies in a tiny region of sky no larger than a grain of sand held at arm's length. Webb's deep fields extend this legacy, penetrating even farther into cosmic time. SMACS 0723 was chosen carefully for Webb's first deep field. This massive galaxy cluster contains hundreds of galaxies, with a combined mass exceeding 1,000 trillion times the mass of our Sun. Such enormous mass warps space-time itself, bending light from more distant galaxies behind the cluster. This gravitational lensing effect magnifies background galaxies, making faint, distant objects appear brighter and larger than they would otherwise, a cosmic telescope created by gravity itself. In Webb's image, the cluster galaxies appear as bright, well-defined structures in warm tones of orange and yellow, their starlight shifted into the infrared by cosmic expansion. But surrounding these are countless smaller, fainter smudges, background galaxies at much greater distances, some appearing as delicate arcs where extreme gravitational lensing has stretched their images. The deepest exposures reveal galaxies so distant that their light has been traveling for more than 13 billion years, showing them as they appeared just a few 100 million years after the Big Bang. Each of these tiny specks represents an entire galaxy containing billions of stars, stellar nurseries where new suns are being born, perhaps planets orbiting those stars, and vast clouds of gas and dust. Yet from our vantage point, they appear as mere points of light, requiring Webb's infrared vision to detect it all. The image contains objects at every epoch of cosmic history, from nearby galaxies whose details appear crisp and clear to the most ancient systems hovering at the edge of observability. The galaxies in this deep field display a variety of shapes and colors, each telling a different story. Some appear smooth and elliptical, their stars formed long ago, now aging into red giants. Others show spiral structure, with blue-white regions indicating ongoing star formation. Still others appear irregular and chaotic, perhaps experiencing mergers with neighboring galaxies, their structures disrupted by gravitational interactions. This diversity reflects the many pathways galaxies can take as they evolve over cosmic time. Following the release of the first deep field, Webb conducted additional surveys targeting different regions of sky. The JADES program, the JWST Advanced Deep Extragalactic Survey, represents one of the most ambitious efforts, combining deep NIRCam imaging with NIR spectroscopy to study galaxy evolution across a broad range of cosmic time. JADES observations have revealed hundreds of galaxies from the first billion years of cosmic history, providing an unprecedented census of early galaxy formation. Another program, JWST, the Cosmic Evolution Early Release Science Survey, focuses on a region within the extended growth strip, an area previously studied by Hubble and other telescopes. By observing the same sky region with Webb's superior infrared capabilities, astronomers can compare observations and identify galaxies that were too faint or too red for earlier telescopes to detect. JWST has discovered numerous candidate galaxies at redshifts exceeding Z equals 10, showing the universe when it was less than 500 million years old. These deep field observations require extraordinary commitment of telescope time. A single deep field may accumulate 50 to 100 hours of exposure, during which Webb stares unblinkingly at its target, its detectors counting photons one by one. The telescope's position at Lagrange Point 2 provides stable conditions. No atmospheric turbulence, as ground-based telescopes endure, no day-night cycle causing thermal variations. Webb simply observes, patient and tireless, gathering ancient light. The resulting images are not photographs in the traditional sense, but carefully processed data products. Each observation uses multiple filters, capturing light at different infrared wavelengths. These separate images are combined using false color, assigning visible colors to represent different infrared wavelengths, allowing human eyes to perceive structures that would otherwise remain invisible. What appears blue might represent near-infrared light at 1 micron wavelength, green might show 2 micron light, and red might display 4 micron radiation. This color coding reveals important information about the objects. Very distant galaxies often appear distinctly red in these images because their light has been shifted so far into the infrared. Nearby galaxies might show blue star-forming regions and yellow older stellar populations. Dust-obscured galaxies, hidden from optical telescopes, blaze brightly in the infrared, their warmth from star formation shining clearly in Webb's detectors. The depth of these observations strains the limits of what's technologically achievable. Some galaxies detected in Webb's deep fields are so faint they appear with a brightness equivalent to a firefly viewed from across the United States. An almost inconceivable dimness, yet just bright enough for Webb's mirrors and sensors to detect. These are the photons that have traveled farthest, survived longest, carrying messages from the cosmic dawn. Each deep field reveals not just galaxies, but the large-scale structure of the universe itself. The cosmic web of filaments and voids where galaxies cluster along threads of dark matter, separated by vast, empty regions. Even at early times, this structure was already evident, showing that gravity had been organizing matter into a hierarchical pattern from the earliest epochs. Understanding the structure helps astronomers test theories of cosmology and dark matter. When we examine galaxies in Webb's deep fields, we notice immediately that the most distant galaxies look different from those nearby. Modern galaxies, those we see in the more recent universe, often display elegant structures, grand spirals with well-defined arms curling through space, or smooth ellipticals with their orderly arrangement of aging stars. But galaxies from the cosmic dawn appear irregular, clumpy, and chaotic, reflecting the turbulent conditions of the early universe. This difference tells an important story about galaxy evolution. The first galaxies formed in a universe that was smaller, denser, and filled with abundant pristine gas. Dark matter halos were closer together, collisions were frequent, and the entire environment was more dynamic and violent than today's universe. Under these conditions, galaxies couldn't settle into stable spiral patterns. Instead, they remained in constant flux, growing through mergers, accreting fresh gas, experiencing bursts of star formation, and being disrupted by supernova explosions. Webb's observations reveal these early galaxies as compact structures, typically just a few thousand light-years across, tiny compared to the Milky Way's 100,000 light-year diameter. Despite their small sizes, they were forming stars at prodigious rates, often creating stellar mass equivalent to our entire sun in just 1 or 2 years. This rapid star formation made them extremely luminous, punching above their weight in terms of brightness, which is fortunate for astronomers trying to detect them across billions of light years. The morphology, shape, and structure of these galaxies provides clues about how they formed and evolved. Some appear as single, concentrated clumps of light, perhaps representing the first bound collections of stars, the building blocks from which larger galaxies would eventually assemble. Others show multiple bright knots, suggesting several star-forming regions or perhaps multiple proto-galaxies in the process of merging. Still others display elongated or tadpole-like shapes, evidence of gravitational interactions and tidal forces. One striking discovery from Webb's observations is that even at very early times, when the universe was only 300 to 400 million years old, some galaxies already contained substantial stellar populations. This suggests that star formation began earlier than some theoretical models predicted, perhaps within the first 100 to 200 million years after the Big Bang. These early stars enriched their surroundings with heavy elements surprisingly quickly, implying that the first generation of massive stars formed, evolved, and exploded in a rapid sequence. The colors of these early galaxies also provide important information. By measuring brightness in multiple infrared filters, astronomers can estimate each galaxy's age and star formation history. Very blue galaxies are actively forming massive young stars, whose intense ultraviolet and blue light dominates the emission. Redder galaxies might contain older stellar populations, or they might be dusty, with starlight absorbed and re-emitted at longer wavelengths. By studying these colors systematically across large samples, astronomers can trace how typical galaxy properties changed as the universe aged. Webb's spectroscopic observations add another dimension to our understanding. When an IR spec captures a galaxy spectrum, it reveals not just the galaxy's overall brightness, but how that light is distributed across wavelengths. a fingerprint that encodes detailed physical information. Bright emission lines at specific wavelengths indicate the presence of hot, ionized gas, where young stars are forming. The strength of these lines reveals the rate of star formation and the metallicity, the abundance of elements heavier than hydrogen and helium. One particularly important spectral feature is the Lyman alpha line, produced when electrons and hydrogen atoms drop from the second energy level to the first, emitting ultraviolet light at a very specific wavelength. In the early universe, this emission is strong, but the neutral hydrogen pervading space at early times absorbs Lyman alpha photons, creating a characteristic break in the spectrum. By measuring the strength of this break, astronomers can determine a galaxy's redshift with high precision and probe the state of hydrogen gas in the surrounding intergalactic medium. Another spectral signature involves oxygen, carbon, and nitrogen emission lines. These elements weren't present in the primordial universe. They were created inside stars and distributed by supernova explosions. By measuring the strength of these metal lines relative to hydrogen, astronomers determine a galaxy's metallicity, tracing how quickly stellar nucleosynthesis enriched the cosmic environment. Early galaxies show low but measurable metallicities, evidence that several generations of stars had already lived and died even at these early times. The spatial distribution of galaxies also matters. Webb's wide-field surveys show that even in the infant universe, galaxies weren't randomly distributed but clustered together in certain regions. These overdense regions, areas where galaxies congregate more closely, mark the locations of large dark matter halos, which would eventually grow into the massive galaxy clusters we see today. By mapping this clustering at different epochs, astronomers can test theories about how structure formation proceeded and how dark matter is distributed. Some of the most intriguing objects Webb has found are extremely compact, luminous galaxies that don't fit easily into existing categories. These little red dots, as they've been informally called, appear as tiny but bright sources with very red colors. Their nature remains debated. They might be compact galaxies undergoing intense star formation hidden behind dust, or they might contain growing supermassive black holes, or perhaps they represent a transitional phase in galaxy evolution that was previously unknown. The presence of dust in early galaxies came as a surprise to many astronomers. Dust grains, microscopic particles of carbon, silicon, and other elements, form in the outer atmospheres of dying stars and in supernova ejecta. Their presence indicates that stellar processing had already occurred, creating the raw materials for these particles. Dust absorbs ultraviolet and visible light and re-radiates the energy in the infrared, making dusty galaxies appear red and sometimes hiding star formation from optical telescopes. Webb's infrared vision penetrates this dust, revealing hidden stellar nurseries. Each galaxy Webb observes represents a unique evolutionary history, shaped by its dark matter halo mass, merger history, surrounding environment, and chance events. Yet patterns emerge when we study large samples, relationships between galaxy mass and star formation rate, between metallicity and age, between size and brightness. These scaling relations reveal the physical processes that govern galaxy formation, how gas cools and collapses, how stars form and release energy, how supernovae regulate star formation by heating and expelling gas. Inside the hearts of the first galaxies, nuclear furnaces burned with primordial fury. The earliest stars formed from gas composed almost entirely of hydrogen and helium, the only elements created in significant quantities during the Big Bang. This pristine composition made these population 3 stars fundamentally different from stars forming today, including our Sun, which contains measurable amounts of carbon, oxygen, iron, and dozens of other elements forged in previous stellar generations. Population 3 stars, though never directly observed, are predicted by theory to have been massive giants, perhaps 100 to 300 times the mass of our Sun. The reason for this enormous size relates to the gas from which they formed. In modern star-forming regions, elements heavier than helium help gas clouds cool efficiently by radiating energy away. This cooling allows clouds to fragment into smaller pieces, forming smaller stars. But the primordial gas had no heavy elements to facilitate cooling, remaining warmer and forming larger, more massive stellar cores. These massive stars burned with extraordinary brilliance, their surfaces reaching temperatures of 100,000 degrees or more, far hotter than our sun's 10,000 degree surface. They radiated intense ultraviolet light that ionized surrounding hydrogen gas, creating expanding bubbles of plasma. Their lifetimes were brief, perhaps only a few million years, because massive stars consume their fuel at prodigious rates, rushing through their life cycles far faster than smaller stars like our Sun, which will burn for billions of years. Inside these stellar giants, nuclear fusion proceeded through multiple stages. First, hydrogen fused into helium in the core, releasing energy that supported the star against gravitational collapse. When core hydrogen was exhausted, the star contracted and heated until helium could fuse into carbon and oxygen. In the most massive stars, fusion continued through successive stages: carbon to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. Each stage released less energy and proceeded more quickly than the last. Iron posed a fundamental problem. Fusing elements into iron releases energy, but fusing iron into heavier elements requires energy input. It's endothermic. Once a massive star's core converted to iron, no further fusion could occur. The core could no longer generate the pressure needed to resist gravity. In less than a second, the core collapsed catastrophically, rebounding in a supernova explosion that briefly outshone the entire proto-galaxy. This explosion dispersed the star's outer layers, including all the newly created elements, into surrounding space. This supernova enrichment transformed the chemical composition of the early universe. Gas clouds that previously contained only hydrogen and helium now incorporated carbon, nitrogen, oxygen, silicon, iron, the building blocks of planets and life. Subsequent generations of stars forming from this enriched gas became population 2 stars with measurable metallicities. Our Sun, forming much later from well-enriched material, is classified as a population 1 star, containing about 2% heavy elements by mass. Webb's spectroscopic observations can detect the signatures of these heavy elements in distant galaxies. Oxygen produces bright emission lines in the infrared when ionized by young stars. Carbon shows up in several forms, both in emission from hot gas and absorption in cooler regions. Iron, though harder to detect directly, influences the overall spectrum and can be measured through careful analysis. By quantifying these elemental abundances, astronomers reconstruct the chemical evolution of early galaxies. Some of Webb's most distant galaxies already show evidence of chemical enrichment, indicating that the cycle of star formation, evolution, and death had proceeded through multiple iterations even at these early epochs. This rapid enrichment implies that the first stars formed very early indeed, perhaps within 100 million years of the Big Bang, and evolved quickly enough to pollute their environments before the universe reached 300 to 400 million years old. The pattern of elemental abundances provides additional clues about stellar populations. Oxygen and carbon are produced copiously in massive stars and dispersed by supernova explosions. Nitrogen forms through different nucleosynthetic pathways, often in intermediate mass stars. Iron comes primarily from type I supernovae, which occur when white dwarf stars and binary systems accrete matter and explode. By measuring the relative abundances of these elements, astronomers can infer the types of stars that contributed to the enrichment. One particularly interesting discovery from Webb involves the detection of highly ionized gas around some early galaxies. This gas emits light at specific wavelengths corresponding to oxygen, neon, and other elements stripped of multiple electrons, a state requiring extremely energetic radiation. Such ionization could be produced by massive young stars, but it might also indicate the presence of accreting black holes, which generate intense radiation as matter spirals inward. Distinguishing between these possibilities requires careful spectroscopic analysis. The earliest galaxies also show evidence for dust formation. Dust grains, though tiny, have enormous effects. They absorb and scatter starlight, redden colors, and influence how gas can cool and collapse to form new stars. Detecting dust in galaxies when the universe was less than 1 billion years old implies that enough stellar processing had occurred to create not just heavy elements in gas form, but also the conditions for those elements to condense into solid particles. Different elements condense into different types of dust. Carbon forms graphite and various carbonaceous compounds, including polycyclic aromatic hydrocarbons that produce distinctive infrared emission features. Silicon and oxygen combine to create silicate grains, similar to the dust found in our solar system. Iron can exist as tiny metallic particles or incorporated into silicate crystals. Each dust type has different optical properties, absorbing and emitting at different wavelengths, creating spectral signatures that Webb can detect. The presence of dust affects how we interpret observations. A dusty galaxy might appear redder than its stellar population would suggest because dust preferentially absorbs blue and ultraviolet light. Star formation rates inferred from ultraviolet emission might be underestimated if much of that light is absorbed and re-emitted in the infrared. Webb's multi-wavelength observations help astronomers account for these effects, building more accurate pictures of what early galaxies were truly like. Chemical evolution continues throughout cosmic history. Each generation of stars incorporates elements from previous generations, gradually increasing metallicity. By observing galaxies at different epochs, comparing those at z equals 10 to those at z equals 5, z equals 2, and z equals 0 today, astronomers trace this enrichment over time. The trend is clear. Metallicity increases as the universe ages, as more stellar generations contribute their nucleosynthetic products. However, the details vary between galaxies depending on their star formation histories and whether they experience inflows of pristine gas or outflows that remove enriched material. Understanding chemical evolution connects directly to questions about life. The atoms in our bodies, carbon in our proteins, oxygen we breathe, calcium in our bones, iron in our blood, were all forged in stellar furnaces billions of years ago. By studying when and how these elements first appeared in the universe, we trace our own cosmic origins, following the chemical threads that eventually led to planets, oceans, and living things. Webb's observations of the first galaxies represent early chapters in that story, showing when the periodic table began its journey from simple to complex. Among the most astonishing discoveries enabled by Webb are observations of supermassive black holes existing when the universe was remarkably young. Black holes form when massive stars collapse, creating regions of space-time so warped that not even light can escape. A typical stellar mass black hole might weigh 10 to 50 times the Sun's mass. But at the centers of most galaxies, including our own Milky Way, lurk far more massive objects, supermassive black holes containing millions or even billions of solar masses. The Milky Way's central black hole, Sagittarius A*, weighs about 4 million times the Sun's mass. This enormous object influences the orbits of stars near the galactic center, which astronomers have tracked for decades, watching stars whip around invisible mass in elliptical paths that take years or decades to complete. These observations provided definitive proof that black holes exist at galactic centers, confirming predictions from Einstein's general relativity. But how do such massive black holes form? And how do they grow so large so quickly? These questions have puzzled astronomers for decades, and Webb's observations have brought new urgency to the mystery. The telescope has discovered quasars, extremely luminous objects powered by actively feeding supermassive black holes, at redshifts exceeding Z equals 10, showing them when the universe was only 400 to 500 million years old. Some of these black holes already contain hundreds of millions or even billions of solar masses. The problem is one of time. Black holes grow by accreting matter, pulling in gas, dust, and occasionally stars from their surroundings. But there are limits to how fast a black hole can grow, set by physics. As matter spirals inward, friction heats it to millions of degrees, causing it to radiate intensely. This radiation exerts pressure outward, pushing against infalling material. The balance between gravitational pull and radiation pressure defines the Eddington limit, the maximum rate at which a black hole can steadily accrete. If black holes grow at the Eddington limit, starting from a stellar mass seed of perhaps 100 solar masses, it would take several hundred million years to reach a billion solar masses. But some of the black holes Webb observes existed when the universe was younger than this growth timescale allows. This timing problem suggests that either black holes grew faster than the Eddington limit permits, perhaps through intermittent super-Eddington accretion, or they started from much more massive seeds, formed through some process other than simple stellar collapse. Several formation scenarios have been proposed. One possibility involves direct collapse of massive gas clouds into black holes without first forming stars. If a pristine gas cloud accumulated enough mass, perhaps 100,000 solar masses or more, it might collapse directly into a black hole, bypassing the stellar phase entirely. This could provide the massive seeds needed for rapid growth. However, creating the conditions for direct collapse requires specific circumstances, and it's unclear whether these conditions were common in the early universe. Another scenario involves dense stellar clusters where stars form so close together that they frequently collide and merge, building up a very massive star that then collapses into a black hole of perhaps 1,000 to 10,000 solar masses. Starting from such larger seeds would reduce the growth time needed to reach supermassive scales. Alternatively, remnants of population 3 stars might have been more massive than typical stellar black holes, providing intermediate mass seeds. Webb's spectroscopic observations help constrain these scenarios by measuring black hole masses in distant quasars. The technique relies on observing broad emission lines in the quasar spectrum. Gas moving rapidly in the gravitational field close to the black hole produces Doppler-shifted emission that broadens spectral features. By measuring this broadening and estimating the size of the emitting region, astronomers can calculate the central mass using Kepler's laws of orbital motion. These measurements reveal that some early quasars harbor billion solar mass black holes at Z equals 10 or even higher redshifts. Such massive objects challenge our understanding of black hole growth and raise questions about the relationship between black holes and their host galaxies. In the modern universe, a tight correlation exists between supermassive black hole mass and the properties of the host galaxy's central bulge. This relationship suggests that black holes and galaxies co-evolve, influencing each other's growth through feedback processes. Black hole feedback occurs because actively accreting black holes don't consume all infalling material. Some is ejected in powerful winds and jets that can heat and expel gas from the galaxy. This energy injection can halt star formation by removing the cold gas needed to make new stars, or by heating remaining gas so it cannot collapse. In this way, black holes regulate their own growth and that of their host galaxies, potentially explaining observed correlations between black hole mass and galactic properties. However, the early quasars Webb observes appear to violate these correlations. Some have black holes more massive than expected for their relatively small host galaxies. This suggests that coevolution relationships took time to establish, and in the early universe, black holes could grow disproportionately large compared to their hosts. Understanding how this relationship developed over cosmic time is an active area of research that Webb's observations are helping to illuminate. Quasars also serve as cosmic lighthouses, illuminating the universe at great distances. A single quasar can outshine its entire host galaxy, making it detectable across billions of light years. By studying the light from distant quasars, astronomers probe the intervening space, looking for absorption signatures created when light passes through clouds of hydrogen and other elements. These absorption systems trace the distribution of matter between us and the quasar, mapping the cosmic web at different epochs. One particularly important application involves studying the intergalactic medium during the epoch of reionization. As the first stars and quasars formed, their ultraviolet radiation began ionizing neutral hydrogen throughout space. By observing quasars at different redshifts, astronomers can trace how this ionization progressed, watching the universe transform from neutral to ionized. The spectra show characteristic absorption patterns that change with redshift, revealing the timeline of reionization. Webb has also observed smaller, less luminous black holes in early galaxies, objects too faint to be classified as quasars but still actively accreting. These observations suggest that black hole formation was common in the early universe, not limited to rare, massive objects. Many early galaxies may have harbored growing black holes, contributing to reionization and chemical enrichment alongside stellar populations. Understanding the typical black hole occupation fraction, what percentage of early galaxies contained active black holes, helped constrain formation scenarios. The connection between black holes and galaxy evolution extends to morphological considerations as well. Simulations suggest that black hole feedback can drive powerful outflows that reshape galaxy structure, potentially suppressing or enhancing star formation in different regions. Observational evidence for such outflows has been found in some early galaxies, where spectral features show gas moving at thousands of kilometers per second, speeds that can only be explained by energetic processes like black hole accretion or intense star formation. As we journey through cosmic history with Webb as our guide, we reach a pivotal transformation, the epoch of reionization, when the universe shifted from a dark, neutral state to the transparent, ionized cosmos we inhabit today. This transition, occurring roughly between 400 million and 1 billion years after the Big Bang, fundamentally altered the universe's properties and set the stage for all subsequent structure formation. After recombination, when electrons combined with protons to form neutral hydrogen atoms 380,000 years after the Big Bang, the universe became transparent to light. But it was also dark. No stars yet existed to illuminate space. The cosmic dark ages lasted until gravity assembled enough mass to ignite the first nuclear fires. When those first stars blazed to life, they began transforming their surroundings, emitting intense ultraviolet radiation that stripped electrons from nearby hydrogen atoms, reionizing the gas. Individual stars create small bubbles of ionized hydrogen around themselves. As more stars formed and died, these bubbles expanded and merged, gradually ionizing larger volumes. The process was not uniform. Some regions had higher star formation rates and ionized earlier, while others remained neutral longer. Eventually, the expanding ionized bubbles overlapped, and the last neutral regions disappeared. The universe became fully ionized, as it remains today, with free electrons and protons pervading intergalactic space. Determining when and how reionization occurred requires observing the universe at high redshifts and looking for signatures of neutral hydrogen. One powerful technique involves studying the Lyman alpha forest, a pattern of absorption lines created when light from a distant quasar passes through intervening hydrogen clouds. Each cloud absorbs light at the Lyman alpha wavelength, redshifted according to the cloud's distance. The resulting spectrum shows numerous absorption features forming a forest of lines. The properties of this forest change with redshift. At low redshifts, corresponding to the recent universe where hydrogen is fully ionized, the forest shows sparse absorption from occasional dense clouds. At higher redshifts, during and before reionization, the forest becomes thicker, more absorption, stronger features, indicating increasing neutral hydrogen. At the highest redshifts, beyond Z equals 6 or so, quasar spectra show complete absorption at wavelengths shorter than Lyman alpha, creating a Gunn-Peterson trough that indicates substantial neutral hydrogen. Webb's spectroscopic capabilities enable detailed studies of the Lyman alpha forest at unprecedented redshifts. By observing multiple quasars at different distances, astronomers map how neutral hydrogen abundance changed with time, constraining the timeline of reionization. These observations suggest that reionization was a gradual process, largely complete by Z is almost equal to 6, about 1 billion years after the Big Bang, but with pockets of neutral hydrogen possibly persisting slightly longer in underdense regions. The sources of ionizing radiation are a crucial question. Early stars certainly contributed. Massive population 3 and early population 2 stars emit copious ultraviolet photons. But were stars alone sufficient to reionize the universe? Or did quasars and actively accreting black holes play a significant role? This question remains debated, and Webb's observations are providing new constraints. By counting galaxies at high redshift and estimating their star formation rates, astronomers can calculate the total ultraviolet luminosity produced by stellar populations. If enough of these photons escape from galaxies into intergalactic space, rather than being absorbed by dust or gas within the galaxies, they could have ionized the universe. However, the escape fraction of ionizing photons is difficult to measure directly because neutral hydrogen within and around galaxies absorbs most of this radiation. Webb has detected signatures of escaping ionizing radiation in some early galaxies, showing that at least some systems had significant escape fractions. These observations suggest that a population of small, young galaxies with low metallicity and dust content might have been the primary drivers of reionization. Such galaxies would have ionized channels in surrounding gas, allowing their ultraviolet photons to propagate into the intergalactic medium. Quasars also emit ultraviolet radiation and were certainly present during reionization. However, current observations suggest that quasars were too rare at the earliest epochs to dominate the ionizing budget. There simply weren't enough of them. Their contribution likely grew over time as more supermassive black holes formed and became active. By the end of reionization, quasars may have contributed significantly, but the early phases seem to have been driven primarily by stars and galaxies. Another aspect of reionization involves its topology, the geometric pattern of ionized and neutral regions. Simulations suggest that reionization proceeded in an inside-out fashion, with overdense regions containing many galaxies ionizing first, while underdense voids remain neutral longer. This created a complex, bubble-like structure where ionized regions surrounded galaxy concentrations separated by neutral zones. Only late in the process did these bubbles merge into a uniformly ionized state. Webb can probe this topology by looking for clustering in the spatial distribution of high redshift galaxies. If reionization was patchy, galaxies should show enhanced clustering on scales corresponding to ionized bubble sizes. Observing such clustering provides indirect evidence for the reionization topology and helps validate simulation predictions. Early results show suggestions of enhanced clustering, consistent with a patchy reionization scenario, though larger samples are needed for definitive conclusions. The epoch of reionization also affected subsequent galaxy formation. Once the universe became ionized, the ionizing background radiation heated intergalactic gas, making it harder for that gas to collapse into low-mass dark matter halos. This photoheating likely suppressed formation of the smallest galaxies, creating a lower mass limit below which galaxies could not efficiently form. This process may explain why the number of dwarf galaxies observed in the local universe is lower than simulations of dark matter alone predict. Temperature fluctuations in the reionization era universe left imprints that Webb can study. As ionized bubbles expanded, they heated surrounding gas, creating temperature variations that influenced subsequent structure formation. These temperature differences affected how gas cooled and where stars formed, potentially creating correlations between early reionization history and later galaxy properties. Detecting such correlations requires comparing maps of reionization with maps of galaxy density at later times. One of Webb's unique contributions involves identifying reionization-era galaxies, those existing during the epoch when reionization was actively occurring. These galaxies are both agents of reionization, producing the ionizing photons, and witnesses to the process, surrounded by a changing intergalactic medium that affected their evolution. By studying hundreds of such galaxies, astronomers can build statistical pictures of typical properties, star formation rates, and luminosities during this crucial transition. Spectroscopic observations of reionization-era galaxies reveal their detailed physical conditions. Emission lines show high ionization states, indicating intense radiation fields. Metallicities are low but measurable, confirming that chemical enrichment had begun. Some galaxies show evidence for powerful outflows, where stellar winds and supernovae drive gas out of the galaxy at hundreds or thousands of kilometers per second. These outflows may have helped ionizing photons escape by clearing channels through surrounding gas. The completion of reionization marked the end of the universe's adolescence. By Z=6, the cosmic dark ages and reionization epoch had concluded. The universe was now transparent, ionized, and filled with galaxies in various stages of assembly. Structure would continue forming and evolving for billions of years, building the cosmic web of filaments and clusters, assembling ever larger galaxies through mergers, and eventually forming the rich variety of galactic types we observe in the nearby universe. But the fundamental transformation from darkness to light was complete. Zoom outward now, pulling back from individual galaxies to view the universe on its grandest scales. What emerges is a structure of breathtaking complexity. The cosmic web, a vast network of filaments, walls, and voids that spans billions of light years. Galaxies are not scattered randomly through space, but organized along threads of dark matter, clustered at intersections, leaving enormous empty regions in between. This architecture reflects the universe's fundamental nature, shaped by gravity acting on tiny density fluctuations imprinted during cosmic inflation. The cosmic web's origin traces back to the universe's first fraction of a second, when quantum fluctuations in the inflating cosmos created regions slightly denser or less dense than average. These tiny variations, less than 1 part in 100,000, were stretched by inflation to cosmic scales, becoming the seeds of all structure. We observe these primordial fluctuations imprinted in the cosmic microwave background as faint temperature variations across the sky. After inflation and recombination, gravity began amplifying these density differences. Slightly overdense regions attracted more matter, growing denser still. Dark matter, unaffected by radiation pressure that temporarily resisted the collapse of ordinary matter, began clustering first, creating gravitational potential wells. Once the universe cooled enough for matter to dominate over radiation, about 50,000 years after the Big Bang, ordinary matter began falling into these dark matter concentrations, accelerating structure formation. The resulting structure is hierarchical. Small objects form first, then merge to create larger ones, which merge again into still larger structures. This bottom-up assembly continues today, with galaxies still falling into clusters, clusters merging into superclusters, building ever larger structures over cosmic time. But the pattern of assembly follows the cosmic Webb template established by dark matter. Webb's observations contribute to mapping this structure by identifying galaxies at various distances and measuring their positions on the sky and in redshift space. Redshift serves as a proxy for distance. More distant galaxies have higher redshifts, allowing astronomers to construct three-dimensional maps showing how galaxies distribute in space. These maps reveal the filamentary structure, with galaxies strung along threads like beads on cosmic strings. Some of the most massive structures in the universe are galaxy clusters, concentrations containing hundreds or thousands of galaxies, bound together by gravity, residing at nodes where multiple filaments intersect. These clusters are among the universe's largest gravitationally bound objects, containing not just galaxies, but vast quantities of hot gas that emits X-rays and surrounding halos of dark matter. The total mass of a large cluster can exceed 1,000 trillion times the Sun's mass. Webb has observed clusters at various redshifts, studying how they evolve over cosmic time. Young clusters at high redshift appear less massive and less relaxed than mature nearby clusters, consistent with hierarchical assembly models. The galaxies within high redshift clusters show higher star formation rates than those in nearby clusters, suggesting that the cluster environment affects galaxy evolution, gradually suppressing star formation as clusters age. Between the filaments lie voids, vast, under-dense regions where few galaxies exist. These voids are not completely empty, but contain some galaxies and diffuse gas, just at much lower density than average. Voids expand over time as structure formation pulls matter out of them and onto filaments, creating increasingly large empty volumes. The largest voids span hundreds of millions of light years, dominating the universe's volume despite containing relatively little mass. The contrast between dense filaments and empty voids creates the cosmic Webb's characteristic appearance. In modern simulations that model billions of dark matter particles evolving under gravity, this pattern emerges naturally, matching observed galaxy distributions remarkably well. This agreement between simulation and observation provides strong support for our theoretical understanding of structure formation and the role of dark matter. Dark matter's properties critically affect structure formation. The leading candidate is cold dark matter, particles moving slowly compared to light speed, allowing them to clump on small scales. Alternative theories, such as warm dark matter made of faster-moving particles, would erase small-scale structure, producing a smoother universe with fewer low-mass halos. By observing the abundance of small galaxies and the fine details of the cosmic web, astronomers can strain dark matter properties. Webb's ability to detect faint, distant galaxies helps count low-mass galaxies at various epochs, testing cold dark matter predictions. If cold dark matter is correct, we should see many small halos hosting small galaxies. If warm dark matter is right, small halos would be suppressed. Current observations favor cold dark matter, though some tensions remain between predicted and observed numbers of dwarf galaxies in the local universe. The cosmic web also channels gas flows. Simulations show that fresh gas streams along filaments toward galaxies, providing the fuel for ongoing star formation. This cold mode, accretion delivers gas directly to galaxies without first shock heating it in a diffuse halo. Webb's observations of gas around high redshift galaxies detected through absorption features in quasar spectra, trace these flows, revealing how galaxies acquire the raw materials for making stars. Galaxy interactions and mergers occur frequently where filaments intersect in overdense regions that eventually become clusters. When galaxies collide, their stars rarely collide directly. Space between stars is too vast, but gravitational forces distort galaxy shapes, trigger star formation bursts, and eventually merge the systems into single, larger galaxies. Webb has observed numerous examples of merging galaxies at high redshift, including spectacular systems with tidal tails and bridges of stars stretched between interacting partners. These mergers play a crucial role in galaxy evolution, transforming small spiral galaxies into larger ellipticals, feeding central black holes with gas that sinks to galactic centers and redistributing stars and gas. The merger rate was higher in the early universe when galaxies were closer together, making mergers an important driver of galaxy growth at high redshift. By counting mergers at different epochs, astronomers quantify how galaxy assembly proceeded over time. The large-scale distribution of matter also creates gravitational lensing effects observable with Webb. When light from a distant galaxy passes near a massive foreground structure like a cluster, the cluster's gravity bends the light path, distorting and sometimes magnifying the background galaxy's image. This strong lensing creates spectacular arcs and multiple images, while weaker lensing subtly distorts many background galaxies. By measuring these distortions, astronomers map the distribution of dark matter in the foreground structure. Webb has used gravitational lensing to study cluster mass distributions and to magnify distant galaxies that would otherwise be too faint to observe. Some of the most distant galaxies discovered with Webb were detected behind massive lensing clusters that magnified their light by factors of 10 or more. Without this natural magnification, these galaxies would remain beyond even Webb's capabilities. The cosmic web's evolution continues today and will persist far into the future. As the universe expands and dark energy, the mysterious component causing cosmic acceleration, dominates over matter, structure formation will gradually cease. Filaments will become more tenuous, clusters will grow more slowly, and the web will stretch and fade. Eventually, in the far future, accelerating expansion will drive structures apart faster than gravity can pull them together, and the web will dissolve into isolated islands of galaxies, each receding from the others into an expanding void. As our journey through time with the James Webb Space Telescope draws toward its gentle conclusion, we find ourselves contemplating the profound story these observations reveal, a narrative of transformation from simplicity to complexity, from darkness to light, from uniformity to structure. The universe that emerged from the Big Bang was remarkably simple. Hydrogen, helium, dark matter, and energy, all smoothly distributed except for tiny quantum fluctuations. From these humble beginnings arose everything we see today. Webb's observations of the first galaxies connect us directly to this cosmic origin story. Each ancient photon the telescope captures is a messenger from an era when the universe was fundamentally different, smaller, denser, hotter, and chemically pristine. By decoding these messages, astronomers reconstruct events that occurred more than 13 billion years ago, long before our Sun, Earth, or solar system existed, long before any of the familiar cosmic landmarks we observe in today's universe. The first galaxies were pioneers, assembling from primordial gas in small dark matter halos, igniting the first stars, synthesizing the first heavy elements, ionizing the surrounding hydrogen. These early systems were small and chaotic, but they were building blocks, merging and growing over billions of years into the magnificent galaxies that populate the modern cosmos. The Milky Way itself, our cosmic home, assembled through this process. Hundreds of smaller galaxies merged over time, contributing their stars, gas, and dark matter to the growing spiral structure. Understanding this assembly process helps us understand our own origins. The atoms in our bodies were forged in stellar cores and supernova explosions, many occurring in the early universe. The carbon that forms the backbone of organic molecules, the oxygen we breathe, the calcium in our bones, the iron in our blood, all these elements were created by stars, some perhaps in the very first galaxies Webb now observes. We are quite literally made of stardust, and Webb's observations trace the origins of that dust back to cosmic dawn. The telescope has also deepened mysteries alongside solving them. The unexpected abundance and size of some early galaxies challenges theoretical models, suggesting that star formation began earlier or proceeded more efficiently than anticipated. The presence of massive black holes in the infant universe raises questions about formation mechanisms and growth rates. These puzzles drive new research, prompting refinements to theories and inspiring new observations. Science advances not just by answering questions, but by discovering better questions to ask. Webb's mission will continue for years, perhaps decades, if the telescope remains healthy. Its fuel-free orbit at Lagrange Point 2, maintained by small thruster firings, could be sustained for 20 years or more. During this time, thousands of astronomers worldwide will use the telescope to study topics ranging from exoplanet atmospheres to nearby star formation, from galaxy evolution to cosmology. Each observation adds to humanity's collective understanding of the universe. Future observations will refine measurements of galaxy properties at high redshift, improving statistics and discovering rarer objects. Deeper exposures will push to even higher redshifts, potentially finding galaxies from the first 100 to 200 million years, closer to the moment when the very first stars ignited. Spectroscopic surveys will measure chemical abundances in thousands of early galaxies, tracing cosmic chemical enrichment in unprecedented detail. Studies of the intergalactic medium will map reionization's progress in topology, revealing how the universe became transparent. Webb will also observe in tandem with other telescopes, combining its infrared vision with data from X-ray observatories studying black holes, radio telescopes mapping cold gas, and optical telescopes tracing stellar populations. This multi-wavelength approach provides comprehensive views of cosmic objects, revealing different physical components and processes. Together, these observations build complete pictures of how galaxies form and evolve. Beyond Webb, future telescopes will continue the exploration. Proposed missions like the Nancy Grace Roman Space Telescope will survey larger areas of sky, finding more rare objects and mapping cosmic structure on vast scales. Extremely large ground-based telescopes, now under construction, will provide complementary capabilities, studying individual objects in exquisite detail. And plans already exist for even more ambitious space telescopes, potential successors to Webb that might directly image Earth-like planets or study the universe's very first light. Each generation of telescopes reveals the universe in new ways, discovering phenomena previous generations couldn't imagine. Galileo's small telescope revealed Jupiter's moons and Saturn's rings, transforming our understanding of planetary systems. Hubble showed us the deep universe filled with billions of galaxies and revealed that cosmic expansion is accelerating. Webb now unveils the cosmic dawn, showing us galaxy formation in action. What will future telescopes discover? What questions will they answer? And what new mysteries will they reveal? Perhaps most profoundly, Webb's observations remind us of our place in the cosmic story. We exist in a universe that has evolved for 13.8 billion years, on a planet orbiting an ordinary star in an ordinary galaxy in an ordinary part of the cosmic web. Yet we are also extraordinary, conscious beings capable of understanding our origins, building instruments to observe across billions of light years, and decoding the history written in starlight. We are the universe contemplating itself, matter organized in such a way that it can comprehend the processes that created it. As you reflect on these observations, perhaps drifting towards sleep, imagine yourself among the stars, surrounded by galaxies young and old, witnessing the cosmic dance of formation and evolution. Imagine the first stars blazing to life in darkness, supernovae scattering elements into space, galaxies assembling and merging, structure forming across billions of light years. Imagine the patient telescope floating in the void, its golden mirrors catching ancient photons one by one, building our knowledge of cosmic history one observation at a time. The universe is vast beyond comprehension, old beyond imagination, and filled with wonders we are only beginning to understand. Yet it is also knowable through careful observation, creative theory, and collaborative effort. Humanity has learned to read the cosmic story written in light. The James Webb Space Telescope represents our latest and most powerful tool for that reading, revealing chapters we've never seen before, showing us the universe when it was young, dynamic, and dramatically different from today. As darkness settles and sleep approaches, let these thoughts carry you gently into rest. You are part of this cosmic story, connected through deep time to the first stars and galaxies, made of material forged in their nuclear fires, living in a universe whose history we can trace back to its very beginning. The ancient photons that traveled billions of years to reach Webb's mirrors carry messages about where we came from, how structure formed, and how the cosmos evolved from simplicity to the magnificent complexity we observe today. The universe is still evolving, still forming new stars, still assembling galaxies, still surprising us with discoveries. Our exploration has just begun. Webb's observations mark not an ending, but a new beginning, opening windows to cosmic epochs we've never clearly seen before, setting the stage for future generations to continue the quest for understanding. In the grand cosmic story, this is but one chapter, and many more await. Rest now beneath the same stars whose ancient light has traveled so far to reach us, knowing that somewhere the telescope continues its quiet vigil, watching the cosmic dawn, gathering light for the first galaxies, helping humanity understand the magnificent universe we call home. The story of the cosmos is also your story, written in starlight, revealed through golden mirrors, connecting you across billions of years to the very beginning of all things.